The crossing number of a graph. In graph theory, the crossing number of a graph is the lowest possible number of edge intersections that occur when the graph is drawn on a flat, two-dimensional plane. When visualizing networks or systems, we generally want to draw nodes, vertices, and connections, edges, with as few overlapping lines as possible. The crossing number formalizes this objective. Formal definition. Let G be a graph consisting of vertices V and edges E. The crossing number, denoted mathematically as CR of G, is the minimum number of crossings among all valid drawings of G in the plane. A valid drawing adheres to specific rules. Vertices are distinct points. Edges are continuous curves connecting their endpoints. Edges do not pass through vertices other than their endpoints. At most, two edges intersect at any single crossing point. Key properties and examples. Planar graphs. If a graph can be drawn without any edges crossing, its crossing number is 0, meaning CR of G equals 0. These are known as planar graphs. For example, a complete graph with 4 vertices, K4, is planar. The complete graph, K5, a complete graph where every 5 vertices are connected to each other, cannot be drawn without at least one crossing. Therefore, CR of K5 equals 1. The complete bipartite graph, K3, 3, often known as the utility graph, representing 3 houses connecting to 3 utilities, water, gas, and electricity. This graph also cannot be drawn without an intersection. Thus, CR of K 3, 3 equals 1. According to Kuratowski's theorem, these two graphs, K5 and K3, 3, are the fundamental building blocks of non-planarity. Any graph with a crossing number greater than 0 must contain a structure derived from one of these two. Computational complexity. Determining the exact crossing number of a given graph is notoriously difficult. In computer science, the problem of finding CR of G is NP hard. This means that as the number of vertices and edges increases, the time required to calculate the exact minimum number of crossings grows exponentially. Because of this, algorithms often focus on finding approximations or upper bounds, rather than the exact CR of G for large networks. Practical applications. Understanding and minimizing crossing numbers is critical in several areas of information systems and network design. VLSI design, printed circuit boards. When designing microchips or circuit boards, wire crossings must be minimized. A high crossing number means more layers of material are required to prevent electrical shorts, which increases manufacturing costs and complexity. Network visualization. In software engineering and data analytics, drawing flowcharts, UML diagrams, or social networks with fewer crossings makes the visual data significantly easier for humans to read and interpret. Transportation and infrastructure. When modeling road networks, train lines, or pipeline systems, edge crossings represent intersections or the need for expensive infrastructure like bridges and tunnels. Minimizing CR of G helps optimize these physical routes.